Did you know that a cloud can weigh more than 1,000,000 pounds? It's like having 100 elephants floating in the sky. It's mind-boggling, isn't it? That's the fascinating world of climatology for you. It's full of surprises and wonders that you might not even have imagined. So are you ready to dive deeper, to unravel more such amazing facts and understand the intriguing science behind our climate? Now that we have your attention, buckle up for an exciting journey into the world of climatology. Imagine wearing a thick fur coat at the equator. You'd melt, right? That's because of the temperature and pressure belts. Now, let's dive into the sauna that is our planet. Our globe is neatly wrapped in temperature belts, starting with the hot, torrid zone at the equator, bookended by two temperate belts, and finally, the frigid polar zones at both ends. It's like a cosmic layer cake, but it's not the kind you'd want to eat. Pressure belts, on the other hand, are like the world's own natural air conditioning system. Starting from the equator, we have the low pressure belt, a hotbed for tropical rainforests. Then we have the high pressure belts, responsible for the world's deserts. Finally, the polar regions again with low pressure. So, these belts play a vital role in determining our climate, weather patterns, and indeed our very lives. So remember, no fur coats at the equator, okay? Ever wondered how Mother Earth manages her heat expenses? She has a budget, you know. Just like we balance our finances, Earth has a heat budget to maintain. This budget is all about balance between the incoming solar energy and the outgoing heat energy. The sun, our generous benefactor, provides Earth with solar energy. This energy is partially absorbed by the Earth's surface, warming it up, while the rest is reflected back into space. Now Earth isn't a miser, she gives back too. The warmed-up surface releases the absorbed heat back into the atmosphere in the form of long-wave radiation. But not all of it escapes back into space. Some is trapped by greenhouse gases, keeping our planet comfortably warm. So, while Earth receives and loses heat, she ensures the budget evens out over time. This balance is crucial for maintaining the planet's average temperature and for supporting life. And that, folks, is how Earth balances her heat checkbook. The atmosphere is not just empty space, it's a busy highway with its own traffic rules. And that's where atmospheric circulation comes in. Imagine the Earth as a giant thermal engine, with the equator as the hot boiler and the poles as the cool condensers. The heat from the equator rises, travels towards the poles, cools and descends, creating a continuous loop of air movement. This is the macro circulation, the grand conveyor belt of our planet's atmosphere. But let's zoom in a bit. Stability in the atmosphere is key to our weather patterns. A stable atmosphere resists vertical movement of air, leading to calm, fair weather. An unstable atmosphere, on the other hand, encourages vertical air movement, often resulting in storms and other weather phenomena. So, the atmosphere is a fascinating blend of orderly circulation and dynamic stability, a subtle dance between heat and cold, stability and instability. So next time you feel a breeze, know that it's just the atmosphere commuting to work. Ever felt a sudden gust of wind and wondered where it came from? It's just the Earth sighing. But hold on, it's not just a sigh, it's a complex dance of atmospheric dynamics. Let's talk winds, monsoons, and jet streams. Planetary winds? They're the big players born from the sun's heat and Earth's rotation. They don't just blow around aimlessly, they follow specific patterns, like the trade winds, westerlies, and polar easterlies. Then there are local winds, the charming characters of our story. They're like the planetary wind's quirky cousins, shaped by local geography and temperature changes. Ever heard of the sea breeze or mountain winds? That's them. Monsoons? Well, they're the drama queens, marking their grand entrance with heavy rainfall. Originating from seasonal wind shifts, they're truly a spectacle of nature. Lastly, the jet streams, Earth's high-speed highways, cruising around at altitudes over 30,000 feet, guiding our weather patterns. Remember, every breeze has a story to tell. From the stirring winds to the silent ocean currents, let's now ascend into the atmospheric battleground where air masses collide and weather is born. Welcome to the world of air masses, fronts, cyclones, and precipitation. An air mass is a large body of air with uniform temperature and moisture characteristics. When contrasting air masses meet, they form a front. Depending on the nature of their meeting, we classify them as cold fronts, warm fronts, stationary fronts, or occluded fronts. Each brings its own unique weather patterns, from rain showers to thunderstorms or even clear skies. Now let's add a spin to things. Cyclones, the swirling beasts of the atmosphere. Temperate cyclones, also known as extratropical cyclones, are born in the mid-latitudes where polar and tropical air masses clash. These cyclones can bring a variety of weather conditions, from heavy rain and snow to clear, cool weather. On the other hand, tropical cyclones, including hurricanes, typhoons, and cyclones, form over warm ocean waters near the equator and can cause severe destruction with their strong winds and heavy rainfall. Speaking of rainfall, it's one form of precipitation, the general term for any water, liquid or solid, falling from the sky. It's not just rain but also includes snow, sleet, and hail. Precipitation patterns vary globally based on factors like temperature, air pressure, and geographical features. So whether it's a drizzle in Dublin, a snowfall in Sapporo, or a hailstorm in Houston, it's all part of the fascinating world of precipitation. From air masses and fronts to cyclones and precipitation, it's clear that our atmosphere is a dynamic and complex system, with each component playing a vital role in shaping our climate. From the breezes above, let's dive into the world beneath the waves. Welcome to the realm of ocean currents, the silent movers of our climate system. These are continuous, directed movements of ocean water generated by various forces such as wind, temperature, and salinity differences. Picture them as underwater rivers, flowing within the vast ocean. They play a significant role in distributing heat around the planet, making them a vital cog in the Earth's climate machine. There are two types of currents: surface currents, which occur in the upper 400 meters of the ocean, and deep water currents, lurking below. Surface currents, primarily driven by winds, are responsible for about 10% of the ocean's water. They're the ones you'd experience if you were to take a dip in the ocean. Deep water currents, or thermohaline circulation, on the other hand, are driven by differences in water density, affected by temperature and salinity. They control the remaining 90% of the ocean's water, and are a key player in regulating Earth's climate over long periods. The warm Gulf Stream current, for example, is the reason why Europe enjoys a milder climate than other regions at the same latitude. Meanwhile, the cold Labrador Current was infamous for carrying icebergs into the path of the Titanic. So, next time you're at the beach or sailing across the sea, remember there's a whole world of motion beneath you, silently shaping our climate. From the winds above to the currents below, it's all interconnected in the grand scheme of our planet's climate system. Scene script. Is it going to be sunny today, or will it rain cats and dogs? Let's ask the weather and climate. Picture this. Weather is like your day-to-day mood, while climate is more like your overall personality. Weather describes the atmospheric conditions at a specific place and time, like temperature, humidity, wind velocity, and precipitation. It can change rapidly from sunny to stormy within hours. Climate, on the other hand, is the average weather pattern in a region over long periods, typically over 30 years. It's more consistent, like the unchanging backdrop of a theater stage where the weather performs its daily drama. Now let's dive into the world of climate classification. This is where things get really interesting. We have three major systems by Köppen, Thornthwaite, and Trewartha, each with its own unique approach. The Köppen system, developed by a German scientist named Vladimir Köppen, is based on the concept that native vegetation is the best expression of climate. He identified 5 major climate types: tropical, dry, mild mid-latitude, severe mid-latitude, and polar. Thornthwaite's system, on the other hand, focuses on the water balance, considering potential evapotranspiration along with precipitation. It's a measure of the moisture a region can supply, contrasted against the moisture it actually does. Last but not least is Trewartha's system. It's a modification of Köppen's, designed to be more applicable to the natural vegetation criterion. It reduces the significance of the summer month criterion and places more emphasis on total annual heat and cold. While these systems might seem daunting, they're like the rule book for Earth's climate, helping us understand the complex interplay of factors that shape the world's climates. They're the keys to predicting patterns, from the mundane, like whether to carry an umbrella today, to the critical, like how climate change might affect future generations. So, knowing the climate can save you from a surprise shower or sunburn. Water everywhere, but where does it all come from? Let's dive into the hydrological cycle. It's a fascinating process that involves the continuous circulation of water in the Earth atmosphere system. It starts with evaporation, as the sun's heat transforms water from oceans, lakes, and rivers into vapor. This vapor ascends into the atmosphere where it cools and condenses to form clouds. And then comes the magic of precipitation. The condensed water droplets in the clouds become too heavy to stay aloft and fall back to Earth as rain, snow, or other forms of precipitation. This water, once on the ground, either evaporates again, gets taken up by plants, or finds its way back to the ocean, completing the cycle. But the story doesn't end there, folks. Our hydrological cycle is intimately connected with global climatic change. As our planet warms due to increased greenhouse gases, the hydrological cycle intensifies. Warmer air holds more moisture, leading to more intense rainfall and snowfall events. But paradoxically, it also causes more evaporation, leading to drier soil and increased risk of droughts. Now you might wonder, what can we, as humble inhabitants of this planet, do about it? Well, there's a lot we can do. We can reduce our carbon footprint by using renewable energy, eating less meat, reducing waste, planting trees, and many other actions. But perhaps most importantly, we need to support policies and companies that are dedicated to reducing greenhouse gas emissions. These changes won't just help slow global climatic change, they'll also protect our water resources, ensuring that the water we drink, the water we use to grow our food, and the water that supports our ecosystems, continues its incredible journey through the hydrological cycle. So, the next time you enjoy a glass of water, remember its incredible journey. Ever noticed how cities feel hotter than the countryside? That's the urban heat island for you. You see, applied climatology is the practical application of climatological knowledge to address real-world problems. It's like taking all the concepts we've been discussing and putting them to work. And one of the most fascinating areas of applied climatology is the study of urban climate. Cities create their own microclimates, known as urban heat islands. Picture a city as a bustling hub of concrete, asphalt, and steel. These materials absorb and store heat during the day and release it at night, causing cities to be warmer than their surrounding rural areas. The urban heat island effect can increase the energy demand for cooling in the summer, exacerbate air pollution, and negatively impact human health. Understanding these urban climates and developing solutions to mitigate the urban heat island effect is a key aspect of applied climatology. So, cities are like giant radiators but with more skyscrapers. Well, we've had quite a journey through the world of climatology, haven't we? We've traversed the temperature and pressure belts, calculated the Earth's heat budget, and even weathered storms of atmospheric circulation. From monsoons to jet streams, precipitation types to climate classifications, we've covered it all. We've even dived into the hydrological cycle and climate change, and explored the realms of applied climatology and urban climate. So, if you found this video cooler than a polar bear's toenails, hit that subscribe button and join us on more exciting adventures.